happy to have Jeevan giving his third and final installment of series of lectures on thin shells and black holes.
Okay, so this is my final lecture. In the interest of time, in this lecture, I don't think I'll be able to get into too many calculation details, but I'll be able to give brief sketches of various calculations. Okay, so let me remind you again that the goal was to show that thin shell black holes and wormholes in ADS3 correspond to statistics of line defects in 2D CFT. And the way to approach this is in two steps to show that you can reduce the gravity problem to an appropriate Liouville problem, and the Liouville problem also the same Liouville problem also gives you the universal dynamics of line defects in 2D CFT. So that was the approach. Okay, so with that we started studying line defects in Liouville CFT. So we showed how to evaluate correlators of this particular line defect, which can be expressed as a continuous product of Liouville vertex operators, and we evaluated these correlators by gluing hyperbolic surfaces. And I gave you an example, the simplest example, where you compute the vacuum one point function of the line defect by calculating the Liouville action on this hyperbolic surface. Or equivalently, you can draw it in the sphere sphere conformal frame, where you are just gluing two hyperbolic disks across the line defect L sigma. And we solved the gluing problem by using these two simple gluing conditions. That is, the Liouville field has to be continuous across the defect, and the jump in the normal derivative of the Liouville field should be equal to the mass of the defect. Okay, so those were the two conditions, and we explicitly evaluated the one point function and observed some nice features, like it resembles that of a conformal defect when you go to the IR. Okay, so that was where we ended last time. So let me just quickly tell you that you can similarly compute other correlators. For instance, you can compute the 2-point function of the line defect in vacuum. So the path integral that computes the 2-point function is, you can write it in cylinder frame. As you can see, this is a plane with these identifications. So this is really a cylinder, and then I've inserted these line defects at times minus tau naught and tau naught. Okay. So that is a path integral picture, and so you evaluate this correlator by computing the Liouville action on this hyperbolic surface. So this surface is constructed by taking a hyperbolic cylinder that you see, that is the middle part, and then gluing two hyperbolic disks on either ends. So it's basically a cylinder with both of its ends capped off by disks, and the two line defects are here and here. So this is like minus tau naught and plus tau naught here. So you can compute the Liouville action on this surface just by gluing together three different Liouville solutions, and similarly you can evaluate the correlator just like the 1-point function. Okay, so next you can also compute the thermal 2-point function. So that was the vacuum 2-point function, and this is the thermal 2-point function. So for that you have to write, the path integral is to be evaluated on a torus. As you see, there are now two identifications. This edge is identified with this edge, and this edge is identified with this edge. And again, the line defects are inserted at minus tau naught and tau naught, and the size of this the thermal cycle is beta. And okay, so the way to evaluate this correlator is again by gluing two hyperbolic cylinders. So I will take this region to be corresponding to this hyperbolic cylinder, and then the remaining region from here all the way here is another hyperbolic cylinder. So this has height 2 tau naught, and this has height beta minus 2 tau naught, as you can see from here. So this height is 2 tau naught, and the remaining height of the cylinder is beta minus 2 tau naught, and then I glue it across these two defects. So the two circles are the two defects, and then I glue these two cylinders across these defects, and I can compute the Liouville action on the resulting hyperbolic geometry. and that's how we can evaluate the thermal two-point function of the line defect.
So one
Yeah.
thing forgetting, but so this is the Liouville CFT computation.
Yeah.
Now there is a calculation that one can do on the bulk side.
Yes,
Right.
correct.
And these are
Equal.
And that is seen as an actually by computing. Or
Yes, actually by computing. You can compute the on-shell action of the three-dimensional geometry, and then it matches with all these. Yeah.
I see. But is there a proof that this will happen all the time?
Yes, you don't need like the specific Liouville solutions. You can prove it in general that if you have any Liouville solution, it corresponds to a bulk solution. Yeah.
Oh, I see. And that's this what 3D.
Yeah, the diagram that I draw where you take a hyperbolic surface times an interval and then reduce the action of the of 3D gravity on that topology to action of Liouville CFT.
And that is enough to guarantee this.
Yeah, that is enough to guarantee. Yeah, it doesn't. It's not special to shells. You can. You can do it with higher topology like a genus 2 surface, or even with punctures. Yeah. Conical defects. Yeah. Okay, so now.
Can this not be stated as some ADS-CFT statement between Liouville and?
It is ADS-CFT, but it's not like the Liouville CFT is dual to 3D gravity. It's only because this match only occurs when there are two boundaries. Suppose you go to more than two boundaries, like.
I thought all these things are single boundary.
Yeah, so it matches for single bound. So this matches with the action of a two boundary wormhole. All these. Whenever you compute correlation functions on a compact surface like a sphere or a torus, you match it with the two boundary wormhole computation in 3D gravity.
Two boundary wormhole. Oh, I thought it just this calculation with a.
Yeah, because the topology is this back reacted sphere times an interval. So you have two boundaries.
What is happening on the other boundary?
It's the same. It's you have like another copy of this on the other boundary.
I see. So that is the state. That is that arrow. That arrow is the arrow of that.
Yeah, it works for single boundaries and two boundaries.
So single boundary on this side is two boundary on that side.
No. So on gravity side, you can either consider single boundary geometries which are black holes, or two boundary geometries which are wormholes. In that case, it matches with Liouville computations, corresponding Liouville computations, where if you evaluate the Liouville correlator on a compact surface, then it corresponds to a two boundary wormhole. If you evaluate it on a disk or an annulus which has boundaries, then it corresponds to black holes. So yeah. Okay.
And should I think of this compact surface as like a Cauchy surface from the point of view of this bulk geometry? Is that it?
With the interval mean time, yes?
Yeah.
Is that how I should think about this?
Yes, that's right. I mean, maybe you can think of slicing the bulk in where the slices are given by this. Exactly. Yeah, that's right.
And on the boundary, there would be, on the boundary of the two intervals, each in that case corresponding to that, each of them would have one shell. Whereas in the case corresponding to that,
there will be two shells here and two shells here. Yeah. Okay.
The bulk I could ask questions which are kind of single boundary geometries with various, let's say, singularities in the bulk. Dual to, I mean, which end on some boundary locus with some conical singularity or something.
Right.
Now I can ask then what is the putative dual CFT? That's a different question then, right?
Yeah. So if it is not of this topology, like a surface times an interval, then it's not. You can't use Liouville to do the computation. Yeah.
But sorry, I mean then. For example, if you have a sphere with three conical loci meeting in the right, this is something that you talked about earlier.
Yeah.
From what you are saying about Liouville, Liouville, it would have nothing to do with Liouville.
No, I can actually do that computation also in Liouville. So because So that geometry is what? It's a hyperbolic ball, H3, with like 3 conical defects meeting at a point in the bulk, right? So the way I can evaluate it is I can slice this using spheres, right? Then I can reduce the 3D gravity action to a Liouville action on these spheres. And it turns out it's not the conventional Liouville theory, but Liouville theory with opposite sign of the cosmological constant. It's like a positive curvature Liouville theory. So yeah.
I see. So you are saying you should always think of foliating the surface.
Yeah. You think of a clever way to foliate foliate this your geometry so that you can make use of all this nice results from Liouville. That's the idea.
Like slice by slice uniformity.
Yeah, exactly. Because all these slices are equivalent to each other, so you just have to uniformize one of the slices and then use Liouville solution. That's it. But I mean, if that is not true, like if all the slices are not equivalent, then this does not work. Yeah.
Uniformization means choosing.
Just constructing this kind of surfaces. Yeah, that's uniformization.
Well, I mean, I was thinking uniformization is that you can go to a round metric, starting from any metric, at the
By
cost of the
choosing-
Liouville action.
By choosing coordinates. And the y.
Yeah. Okay, so for our purposes, what we want to do now is like we want to relate the Liouville calculations to derive the Cardy formula. So to do that, we have to compute these Liouville correlators in the presence of boundaries, because then I can make the direct connection to the CFT. Because what I'm going to show is that if you take the identity block of the CFT defect and evaluate it on identity block on a sphere, say, and that is proportional to the 1-point function of the line defect on a disk with ZZ boundary conditions. And similarly, the identity block evaluated on a torus is the 1-point function of the defect evaluated on a annulus with ZZ boundary conditions. So these relations are how you can translate Liouville to CFT. Basically, Liouville with ZZ corresponds to something in CFT. So that's the idea. Okay, so in case you are not familiar with ZZ boundary conditions, there are one class of conformal boundary conditions in Liouville CFT. Famously, there are conformal boundary conditions are of 2 families, ZZ and FZZT. So ZZ, for our purposes, ZZ is just a Dirichlet boundary condition for the Liouville field. Because if you want to evaluate Liouville action on surfaces with boundaries, say a disk or an annulus, which have boundaries, so you need to specify what is the boundary condition for the Liouville field on these boundaries. So you can either choose Dirichlet or Neumann among the simplest kinds of boundary conditions, and I'm just using the Dirichlet boundary conditions on any of these boundaries. So
Usually at the weak coupling end or the strong coupling end or somewhere in the middle.
what is the weak coupling end?
Meaning at what value of phi?
Oh, it's near that. This is like the asymptotic boundary. So it's the value of the Liouville field blows up near that. So I'm just fixing the follow.
So that's where the wall is?
Yeah, that's where the
So that's strong coupling.
I see. I see.
So that comes with some boundary cosmological constant?
No, that is the FZZT condition.
is-
That's the Neumann boundary
that's the
condition.
Neumann.
Yeah. Okay.
This F1 is defined in any CFT.
Yes, modulo the subtleties that you people pointed out last time. Yeah. But I guess, I mean, this is really a representation theoretic object because it's, yeah, so maybe those subtleties don't matter. So the subtleties that you guys pointed out last time would matter when I assume that this is the dominant contribution. But these identities are all like mathematical identities.
So very good.
Yeah.
Now that this F1 is a kinematic object,
Yeah.
can we define it?
Yeah.
Yeah, can you just define it again? Because last time it was plagued with all these issues.
Uh-huh.
But if there is, as you say, if there is a clear definition that.
Yeah. I mean, can I do it in like 5 or 10 minutes because I can compute this? Yeah.
And at this stage, there is no averaging on the CFT side.
Sir,
And
someone.
at this stage, there is no averaging on the CFT side.
No. Well, let's not get into averaging right now. All these are like individual CFTs. Yeah. Okay, so let's do the annulus one-point function. Annulus one-point function. So the reason why we want to do this is because we want to evaluate this matrix element. So this matrix element governs the dynamics of the line defect L sigma, and it turns out that the Cardy formula for the CFT line defect is just proportional to this guy. So that will be the key result. And so what we want to do is we want to extract this matrix element by computing the Liouville correlator on the annulus. So as a path integral, what we want to compute is this guy. So let's say this line defect inserted on an annulus of length beta over 2. So I am working in the conformal frame where the annulus is mapped to a finite cylinder. So
H prime could have been states created by local operators also, right?
yeah, there could be operators below the threshold, so you have to like do separate calculations to extract that part. Right now, using the annulus, you can only extract when H and H prime are above the threshold.
That is big holes versus this previously.
Yeah, holes versus points. Yeah.
Okay.
So this is the path integral that I want to evaluate.
It will end up being analytic.
Yeah, it will end up being analytic. I mean, but it's not very easy to prove that it's analytic. It's very tricky. So I won't go into all that. But the key result is, yeah, you have to do separate calculations and then show that it's.
And is this point versus hole also somehow related to this gravity picture of conical defects versus
Higher topology.
higher topologies?
Yeah. The holes create like higher topologies, right? Like genus 2 or whatever. Whereas this conical defects create world lines. Okay, so what is the hyperbolic surface that, I mean, this is always the idea. So write down the path integral that computes it and then identify what is the hyperbolic surface to evaluate the Liouville action. So the hyperbolic surface will look like this. I mean, there are two possibilities. I'll draw one of them. I'll draw both of them. But so this is like the ZZ boundary, and then the surface curves inward and then reaches a minimum radius, and then you insert the line defect, and then again it does the same on the other boundary. Okay, so bad drawing. So there are two minimal geodesics on the surface. So those actually correspond to the saddle point weights, because the saddle point weights are actually related to the length of the geodesics. I mean, this is a non-trivial proof, but I mean, just maybe you can accept it. So there is this nice relation which relates the saddle point weights in the evaluation of the Liouville correlator to the lengths of the geodesics on the hyperbolic surface.
This is just what he said, but I didn't understand. How did H and H prime go? The calculation you did seemed to be specified by boundary conditions and.
Yeah. So this is not the calculation I'm directly doing. I'm doing this path integral.
Yes.
And I can expand this using in terms of by inserting complete set of states. So what I'm actually doing is this calculation. In operator language, I've inserted the ZZ state, I then evolve it by tau naught, then insert the line defect here, and then evolve it by beta over 2 minus tau naught, and then again I annihilate to ZZ.
Yeah. So one point function between them.
Exactly. So the now I insert complete set of states, like maybe here and here. So that's like integral h and here integral h prime. So I mean roughly this is like dh prime times h L sigma h prime times some factors. So what this means is that the saddle in this has to match with the saddle in the Liouville calculation. Because what I'm computing is the saddle point limit of this correlator using by gluing hyperbolic surfaces, and that has to match with the saddle point in the spectral decomposition of the correlator.
I didn't understand how you're going to pull out arbitrary H prime from there.
Because I know this for all values of the parameter tau naught, so I'll trade them. Yeah.
So if you were to directly do it, then would it be fair to say that the H state would be created by a circle of some size, right?
Yeah.
Which is as an embedded surface.
Correct.
As a zero curvature.
Correct. Yeah. Maybe you could try to do it directly.
Just have that middle piece there.
Exactly. Middle. Yeah. Maybe you're saying like from here to here. But sometimes this may not be visible, but still you can compute this, because there are two types of surfaces that compute this. One where these two minimal geodesics are actually visible, and one in which only one of them is visible. Something like this. Like this. Like in other words, you put the boundary here so that it's like on the other side of this geodesic, so that this geodesic is not visible but it's secretly there.
And what is the logic? Sorry, I'm thinking of this H state as this hole eaten out by the black hole kind of.
Correct.
Kind of thing.
Yeah.
Why did it have to be on a geodesic? Its boundary sort of had to be a geodesic.
Is it? Sorry, where is the geodesic?
Well, these are geodesics. I mean, the reason why I say that these are related to geodesics is because of this relation, that the conformal weights are related. Conformal weights in the Liouville correlator are related to the geodesic lens. So that's sort of
The boundaries are not geodesics, right?
These boundaries are not geodesics. Yeah.
No, but the thing he's thinking of is black hole.
Yeah. Exactly.
That was the geodesic, I thought.
Oh, okay.
I mean, roughly speaking, if you evaluate this, there are these phases: ZZ overlap with H, and then H prime ZZ, and then these matrix elements. So I guess very roughly speaking, you could associate this with this part, and then you can associate this with this part, and then associate the matrix element itself with the region in between the geodesics. Yeah, that's rough. That's a rough intuition. Yeah.
Okay. So Shirad, maybe one can think of this Liouville theory as living on a particular slice of 3D gravity.
Of the inside.
Inside 3D gravity, because as you said, it's not area safety.
Yeah.
It's slice by slice.
Yeah.
Correct.
Slice. How are you slicing?
Hyperbolic slicing. For instance, if you have a single. Sir?
A particular R.
No, I think it's a particular.
So suppose if you have H3, so I'm slicing it in such a way that each of the slices are H2.
So I think it's more like a York time slicing or something. Like it's,
Okay, I don't know what it's
constant extrinsic curvature.
Yeah, I mean, so if you have, yeah, so if you have H3, then the way to slice this to obtain these results are like this, something like this. So that each of these slices are hyperbolic disks.
Are they constant extrinsic curvature from the 3D point of view?
Yeah, they should be. They should. Hyperbolic, inside hyperbolic space. Minimal.
I'm not sure because well.
They'll be constant. I feel like there will be constant extrinsic curvature.
Constant extrinsic. Okay, yeah. I mean, it should be easy to check. Yeah, I don't. Yeah.
Oh, and sorry, in the black hole case where you've got this hole punched out through the surface.
Yeah. Yeah.
Now, in that case, roughly what are these slices?
Okay. Yeah. So, which black hole do you want to consider? Like.
Just a BTZ black hole.
Oh, the.
Just one black hole.
Oh, so the. Okay, you don't want shells or anything. Just the BTC black hole.
Whatever is easiest to draw.
Okay, so let's do the BTC black hole. So the BTC black hole is a solid torus.
Yes.
So I can think of the solid torus as an annulus times an interval. So annulus is a finite cylinder times interval. And then I glue these two boundaries asymptotically. So now you see, just forget the bulk, just see the boundary. The boundary has the topology of a torus, and then I'm filling the torus.
Yes.
So this is BTC.
Yes.
So the Liouville solution that will show up here is the Liouville solution on an annulus with ZZ boundaries.
So should I think of the annulus as living at the boundary of?
I mean, each of these slices is an annulus. So I mean, it doesn't matter which where you are solving this Liouville equation, but because all of them are equivalent. Because the metric on this geometry is now of this form. So times e to the phi mod dz squared. So you are uniformizing all the rho equal to constant slices.
So these are torus slices of the BTC black hole, right? Take the boundary.
No, not the torus, because torus does not have a hyperbolic metric.
So it's a constant rho slice.
This is annulus. No.
No, but the whole thing was a torus.
The whole thing was a torus. Yeah.
Now, what slice are you getting the Liouville on? Which part of the solid torus?
Yeah. So okay.
Well, the Liouville. So the boundary is this union this, right? So the two cylinders are glued together to get the torus.
But then you have hyperbolic torus, right? Which as you said doesn't exist.
No, but because there's no this is not a smooth gluing, right?
Oh.
You have like these easy boundaries. This is just a trick. Yeah, it's not. Yeah.
So it's a topologically it's a torus.
It's topologically a torus. Yeah, correct.
I see.
Yeah, that's right. Okay. So the reason why I explained this computation is because I can compute the Liouville action on this surface, and equate that to the spectral decomposition. So
I'm so sorry.
yeah.
So I've got this topologically torus boundary, which I'm thinking of, if you don't mind, as the boundary of the solid torus.
Yeah, that is the boundary.
Okay.
Yeah.
Now there is this black hole, which was the hole eaten through this. You know, the thing that would have become a geodesic had you been below threshold.
Yeah.
Is like this hole eaten through the solid torus. So that part, is there any sense in which I'm seeing it as a hole in this computation? I mean, what I'm asking is, suppose I compare the two things where this was below threshold and this was above threshold.
Which was below the?
So I have my. I'm thinking of my torus as a one-point function, maybe thermal one-point function of a very massive operator. Okay, that has eaten this hole through the torus.
Yeah, so you can. So if you want to compute like thermal correlators, say the thermal 2-point function, so you can puncture this cylinder on both sides, and then there's a particle that goes through. And then if you want to create a hole, then make this push the weight of this operator to above the black hole threshold. Then that will create a hole like this.
No, already that's a geometry of the hole, right? That's a BTZ black hole.
No, but I thought he wanted another hole.
No, I was just trying to understand this hole as compared to a geodesic running through.
Oh, okay. Then what is happening is I have two disks. Okay, then let me explain. So I have two disks times an interval. So this is ADS3, empty ADS3. Now let me say I puncture the disk at one point at let's say the origin, and then that will create a particle that is propagating through. Now I push the weight of this operator to above the threshold so that it will create another boundary.
Right.
So now this is this is BTC.
Right.
Yeah.
And the outside of it though.
Yeah.
So, what are your foliations in this case compared to the other case?
So for the they're the same. The foliations are annulus. Yeah. Yeah. I mean, maybe the confusion was because I drew the annulus in the cylinder frame. I guess, yeah, but. Okay, so I mean, I won't go into like all the details of how to evaluate this calculation, because you just have to solve the gluing condition and then evaluate the on-shell Liouville action on this hyperbolic surfaces, and then you will evaluate the Liouville action, and then you are equating.
When you say that there could be sometimes this horizon is not visible.
Yeah.
Is that the case when H prime below the threshold?
No, that's not true. Even when H prime is above the threshold, you can, I mean, you can, it is possible that the horizon is not visible. Yeah, it's like in 3D gravity, I showed you last time that the shell could be either gone inside the horizon or it could be outside the horizon, but still there is a black hole in, so similarly, it's the similar idea. Whether the horizon is visible or not, it's still like a black hole. Yeah. Okay, so by equating the spectral decomposition of the one-point function to the Liouville action, I can write down an expression for the matrix element.
The horizon is not visible. That's in the Liouville CFT, it's still in the two shape quantifications.
Sir, yeah, it's still Dirichlet boundary conditions.
Dirichlet means phi goes to infinity, right?
In a particular way, like I need to specify like the fall off or growth of the Liouville field. Yeah. Okay, so the final result of this calculation is the expression for the matrix element, and the matrix element has phases. So I won't explain what those phases are, but the expression is just given by the following. So let me call it e to the c over 6 times cl of gamma prime. So these are the structure constants of the line defect, and I am evaluating this in the large C limit. So I am parameterizing this matrix element in this way, where gamma and gamma prime are related to the weights. They're just a convenient way to parameterize the weights. So I can express the, I'm defining that these gammas, which are sometimes called momenta, they are related to the weights by this relation. I mean, you can see why this is useful, because at the saddle it turns out that gamma is just the length of the geodesic. So that's why this parameterization in terms of momenta is very useful. Okay, yeah, here is the expression. Okay. So, if you are familiar with the DSCC formula for local operators, this is the analog of that for line defects. So, Okay, so this is the Liouville structure constants for this line defect. I mean, this is the expression for the matrix elements. So they are functions of two conformal weights and the mass of the defect. So as you can see, they are symmetric under exchange of the two weights, as you would expect. And in fact, this also turns out to be like very closely related to the Cardi formula for these line defects. Okay, so this is the Liouville part of the calculations. So now next I will be going to the CFT part. So if there are any questions about the Liouville, you can ask. Okay, if not, so let's go to the Cardi formula for for the line defects in CFT. So recall that we wanted to understand the dynamics of this line defect that is constructed in CFT. So this line defect was a product of local operators. In the continuum limit. So this is so just like the Liouville defect, this is a product of local Virasoro primary operators, and so in that way, Liouville d sigma is sort of like analogous to the line defect L sigma. So we want to understand the dynamics of this particular line defect. So that's the goal. So the way we are going to do it is to understand how to translate the Liouville calculation that we just did, that is the annulus one-point function, to the identity block on the torus. So to do that, let me first give us a couple of simpler examples. So recall that the vacuum character on the torus in the dual channel can be expressed as a cylinder transition amplitude between ZZ states. I mean, you can explicitly verify this because the expansion of the ZZ states in an appropriate basis is known, and then you can evaluate this matrix element explicitly and check that it gives you the identity character on the torus in the dual channel.
Identity character just means partition function.
No, it's a contribution to the partition function.
Oh yeah, the vacuum block.
Yeah, vacuum block, but with no operators. No external operators. Sorry. Yeah. So in the language of the path integral, what this means is if I am computing the path integral on the torus, so that's sort of equivalent to like taking half of the torus and writing it as a cylinder and then inserting ZZ states. So that's the trick. So the and suppose we want to impose that the identity is running around a cycle of the torus. So all you have to do is you have to cut the CFT path integral in half and then interpret it as a Liouville path integral and evaluate the Liouville path integral to get the CFT answer. So if this was height beta, this would be height beta over 2. So
Channel is identity running.
in the so you are computing the cylinder transition amplitude, right? So where you have ZZ states inserted and the height of the cylinder is beta over 2.
Okay.
So the identity is running in the dual channel because you see there is a minus 1 over tau.
Okay.
Yeah.
But that the dual channel is some boundary state, right?
Yeah.
The Hilbert's
For instance, you could evaluate this cylinder using the boundary channel. Like when I write it this way, I am evaluating it as like a closed string transition amplitude.
Yeah, so in the dual channel it's an open
Yeah, in the dual channel, it's it's like you're quantizing Liouville CFT on a segment, and then you computing the partition
When you
function.
say identity,
Yeah. So that is the result that this is showing. So what this is showing is that if you quantize Liouville CFT on this segment and impose this ZZ type of boundary conditions at the endpoints, then the Hilbert space only consists of the identity and its
identity on the circle.
the identity on the circle. So that's the result. Yeah.
This is some non-trivial statement having, this will require some understanding of ZZ boundary conditions.
Yeah. You need to understand like how to expand this ZZ in the basis of Ishibashi states, and it's a non-trivial condition. Yeah. So this is sort of saying that you can use Liouville to understand the representation theory of 2D CFTs. So that's the upshot. Okay. So this is when there are no external operator insertions. So, but this is also true when you have external operator insertions. For instance, let's say we compute the 2-point function. So in the CFT, what I'm doing is I'm computing the sphere 4-point function between pairs of identical operators. So let's say this is operator 1, 2, and this is operator 1, and this is operator 2. And I want to evaluate the identity block, which means I have to impose that when I cut the path integral around a closed curve which joins these pairs of identical operators, there's an I impose identity. So this is how the identity block is defined. And again, you can use the same trick. So to cut the path integral in half, and then think of this as a Liouville path integral, where I have imposed a ZZ. Actually, this boundary is at infinity because I'm computing it on the sphere. So this boundary is at infinity, so I don't have to impose any boundary. And now I just compute the Liouville 2-point function on a disk. So this is the disk. So the sphere 4-point identity block is equal to the 2-point function on a disk with ZZ boundary conditions. So that's the statement. So the identity block, let me write it this way. So you're computing the identity block between this is in CFT, and this is the identity block, and then I'm saying that this is equal to the Liouville 2-point function on a disk. Okay.
What if 2 is also equal to 1? 2 is 1, then
I mean, still you can define the identity block in this channel, and that is computed by this. I mean, maybe if you want to compute in a different channel when these both are equal, like impose that like.
Yeah, can I think of this as a defect block in the sense that, so usually when you have these boundaries or defects, you can span the Hilbert space by having defect local operators also, the operators that live on the defect.
I see.
Right. So you can now circle that one in a semicircle that intersects the ZZ boundary.
Right.
And then shrink that to a local operator on this thing.
Yeah.
Right, on the defect, and also that.
Right.
And that's the identity block. Then
correct.
The identity block on the defect.
Yeah. I guess you are asking if we can expand this in the boundary channel, in the boundary channel. Yeah.
So when you say that,
so here what we are doing.
Identity channel here is easy like that.
Yeah, so basically this loop becomes this half of this like this.
Yeah, exactly.
Yeah, so we showed that like if you have like if you take a segment with ZZ boundary condition, there's only the identity running, right? So that's the reason why it computes the ZZ boundary conditions computes the identity block. Same reason, like because there's an identity running in this.
You're saying there's only identity running.
There's only identity running. That's the result. You cannot compute other conformal blocks this way. ZZ is like sort of tuned to compute the identity block. That's it.
I see. You're saying ZZ, that's why the ZZ boundary condition is special.
Yeah, it's special.
That it picks out only the identity block along with it.
It picks out the whole identity block.
I see.
Yeah.
Otherwise, I mean, you could have said that for any defect, right? You can take any defect.
Yeah,
as
yeah.
long as you project on the identity block of the defect, that
Correct,
is
correct.
equality.
Correct, yeah.
And Pixar only identity means the only states with those boundary conditions are vacuum and
Vacuum and its descendants. Yeah.
It's not clear. Is it clear?
I mean, I mean, I don't know if you're familiar with that result. Like I can derive that result by expanding the ZZ states using the Shibashi states and then actually evaluating this, and then that's the proof.
No, but just
no,
like if
no
you
boundary
think of it as a-
primaries. There are no boundary primaries.
Yeah.
Right, that's the state.
That's the statement. Yeah.
So somehow because it's at infinity,
What is it?
the boundary conditions are infinite. Phi is at infinity, right? Nothing's happening there.
I mean, if you do like FZZT, so Neumann boundary condition for the Liouville field, that's not true.
Yeah.
But the boundary is still at infinity.
The boundary is still at infinity?
Yeah, it's like boundaries are still at the boundary of the Poincare disk.
Oh, I see.
Yeah. So,
But maybe you held it to be at infinity.
yeah, that's true.
And in the value.
Well, I guess to like.
Value of phi to be held at it.
Is sort of what I don't understand these boundary conditions, but somehow you're saying Dirichlet.
So
you're
I'm
forcing the field to be beyond the wall, right?
Exactly. So,
So
yeah.
that's why it's somehow empty. Is that? Maybe the Neumann part is like a plane wave,
Uh-huh.
which is saying that you've got stuff here, but it also moves there.
I see.
I don't know.
Well, I mean, there is like a generalization of ZZ. So the ZZ is actually a two-parameter family of boundary conditions where they're labeled by a pair of integers. So I took this like when people just say ZZ, they're referring to the family where like you set M and N to be 0, and that corresponds to the identity. But you could consider another state in that family. And in that case, the only operator which is running in this channel would be a degenerate operator with labeled by this two pair of primaries. So
Suppose Abhijit's question can be translated to, can you explain semi-classically why the only operator identity in this? And give some rough intuition. I mean, we normally have Dirichlet boundary conditions. We have e to the power I k dot x or whatever. The Neumann. We have all kinds of primaries on that.
Right.
Why are they missing here? I have normal derivatives of x. Various normal derivatives of x. Oh, is that's not a primary? Maybe that's similar. Sorry, what are the primaries normally with Dirichlet boundaries?
On the defect.
Just take one scale, free scalar field,
Mhm.
put a Dirichlet boundary condition. Now, because we've got a Dirichlet boundary condition, at the boundary x is fixed, so we can't say e to the pi k dot x.
Derivatives, integrals.
Derivatives, but those are descendants, right?
And not from the boundary point of view.
Not from the boundary. So normal derivatives, fine. So there, yeah.
I mean, this is not like the usual identity. This is like Virasoro identity. So it has all the stress tensor contributions here. So it's
Understood.
yeah.
What is the answer to that question for just ordinary boundary condition? Dirichlet boundary conditions. What are the primaries there? The analog of this only vacuum running. So just an interval and Dirichlet boundary conditions
For a free field.
free field.
For free field.
I mean, of course, you've got all the open string oscillators, right?
Yeah.
So it's more than.
It's more than just the vacuum. Yeah.
Okay, so the question, why in this case is it so little?
Yeah, I guess you're asking from an intuitive point of view without a calculation, right?
Yeah. I think nobody doubts the calculation, but roughly.
Something like this open string is becoming, tension is becoming too large.
I mean, that's
That's not the case.
Yeah, I don't think like just relying on semi-classical intuition would help, because as I told you, like ZZ is labeled by there's a family of ZZ boundary conditions, and only a particular member of this family gives identity. The other members of this family give like degenerate primaries running in this boundary channel. So I don't know if I can use like that fact that these are Dirichlet boundary conditions to explain that there is only the identity. So yeah.
What are the other members in family? This one is fixing the Dirichlet boundary condition.
Well, those other members, I don't know if I can write down a semi-classical like boundary condition for the Liouville field. So they are more like you solve the boundary conformal bootstrap exactly, and then you end up with this families of boundary conditions which are ZZ and FZZT. So that's.
But from an EVS point of view, I should think of like this identity block as 1 being joined by some Wilson line or something.
Correct. Yeah. So in the bulk, you have these operators meeting like this.
And then these on the right hand side, these are just these two punctures, right? Like you're thinking of this bulk geometry, slicing it, and then you see these two punctures.
Yes, correct. So in the bulk picture, you have let's say you have hyperbolic ball with the world lengths of two defects. Let's say 1, 1, 2, 2. So this picture is when I slice this using discs. So each of the slice is a twice punctured disc like this. See, each of them is a twice punctured.
No, and the one with the FCCT boundary condition?
I don't know. Yeah, that's a good. That's an interesting open question. What is FCCT like related to 3D gravity? No. Yeah. Well, one thing I can say is that if you compute a cylinder transition amplitude with one, so this is another nice fact. Like one with ZZ and the other with FZZT. Then you can, FZZT is actually labeled by the cosmological constant. So there is like a one parameter family, continuous family of these solutions. And you can actually evaluate the other characters, not just the identity, the non-vacuum characters are also visible. So in other words, if you quantize the Liouville theory with one ZZ on the boundary channel with one ZZ and the other FZZT, you have all the states, not just the identity.
If you have two FCZTs, you expect to have all the states with multiplicity or something like that?
Sorry, yeah. So in this case, there is this family where the states are like a conformal primary, a heavy conformal primary, and its descendants. So that's the states living in this boundary channel. But if you say if I put FZZT here with different values of cosmological constant, then there's like a continuous spectrum. Yeah.
It feels a little bit like, that the ZZ is like a wall of nothing.
Yeah, it's a wall of nothing. Yeah. That's right.
This is a continuum.
This is a yeah.
So if you're getting half,
yeah.
Full, you're very healthy.
Yeah, yeah. It would be nice to understand, like, if there's an intuitive way to like arrive at this. Yeah.
In the bulk, this property is difficult to replicate.
For the FZZT, yeah.
For ZZ boundary condition also.
For ZZ it's easy because the ZZ corresponds to the black hole, right? Because the reason why ZZ is easy because it corresponds to the identity block, and we know that the identity block matches with the black hole and partition functions. Yeah.
So if you can, the locus of this ZZ brane is the horizon.
Locus of the ZZ brane. No, it's not the horizon because the ZZ brane has a very small locus, because once I glue the two boundaries, then the ZZ brane has a very small locus. In fact I have to take it in the limit where the ZZ brane is entirely localized on the boundary. Yeah. In other words, if I do this slicing where all these are disks, so the ZZ brane actually lives here. And I'm evaluating in the limit where this is right at the boundary. Okay, so this was for local operators. Now the same will be true for line defects. So let's say I want to evaluate the identity block for the line for the CFT line defect. I guess this this brings back to Abhijit's question: how do you define the identity block, right? So this is a line defect inserted at tau naught. This is a line defect inserted at minus tau naught. And the way I define the identity block is by projecting onto the identity along any of these rectangular curves. So so this is how I define the identity block.
But so these line defects are not really line defects. There's some limiting.
Yeah. Correct. I mean, so this was true for like 2-point functions. It's also true for 3-point functions. So on in that sense, in the limiting sense, it's true. Yeah. So again, I use the ZZ trick. I cut this in half and put ZZ. So ZZ, I cut then. So this is the 1-point function on a disk. Now for the now we can do the annulus case. So the torus identity block is equal to the annulus 1-point function, because just cut this in half and then again insert a line defect and yeah. So the torus identity block. So we have basically just proved that the torus identity block is the 1-point function of the line defect of the Liouville line defect on the annulus. Okay.
Torus 1-point identity block with the line defects, right?
Yeah, with the line defects. Yes, correct. Yeah. So sorry, I should call it defect identity block. Yeah, because in the presence of line defects. Yeah. Okay. Okay, so now what I can do is I can, so the block has by definition as an expansion in the dual channel with a crossing kernel. So it's very roughly speaking, it's of this form: dh prime. Then there are these factors of rho 0.
Sorry, in the dual channel, where are you inserting complete set of state? The middle line.
Yeah, the middle line. Yeah. Times the fusion kernel, which I call C0D, h comma h prime, times the dual channel conformal block, which let me call it f tilde.
Sorry, but why is there, I mean, two integrals? If you are inserting it at one particular slice, there is only one integral dh, right?
Sorry, on the sphere there is only one integral, but on the torus there are two integrals.
On the torus, I see.
Because you are inserting here and also here.
Oh.
Yeah.
Oh, I see. That's how you are getting that L with here h and h prime there.
Yeah, correct, yeah.
Right, sorry, yes.
Yeah. Okay, so this is the expansion of the identity block in the dual channel. Similar, and we have a very similar expansion for the Liouville 1-point function. So you can expand this as, I mean, this is very schematic. This turns out to be square root rho 0 h, where rho 0 is the Cardy density of states. Square root rho 0 h prime times the 1-point function of the the matrix element of the defect times again the conformal block. So now you see you can get the fusion kernel by matching the these two spectral decompositions, and it turns out that the C0D is actually equal to the matrix element, magnitude of the matrix element, divided by these two Cardy factors, square root rho 0 h, square root rho 0 h. Yeah, so this is the important result. I mean, there's a normalization factor, but you don't have to worry about that. So this is the result, that the fusion kernel that transforms the identity block in the dual channel is given by the matrix element of the Liouville line defect up to all these factors.
Sorry, this is kind of that object, right?
Yeah, this is kind of this is object. So this object is this CL.
Sorry, that L was Liouville.
L was Liouville, yeah. So the left hand side is CFT, right hand side is Liouville. And we have evaluated this by computing the annulus one-point function, and it was given by this. So remember that the way CL was defined was something like this. Yeah, CL. So we evaluated this guy. So we also know what this guy is in the semi-classical limit.
No, but this just like Cardi formula, this should have some range of validity. Right?
Yeah. It should have a range of validity. I mean, I don't. Yeah. So the no, sir. This is a mathematical statement that the fusion kernel is equal to this. But the Cardi formula is a statement about like these discrete matrix elements. That if you have the line defect d sigma, and then I compute the matrix element between heavy states, and when is this approximately equal to this? So when is this approximately given by the fusion kernel, where Hi and Hj. So this is Cardi formula. So this is Cardi formula. So Cardi formula is the statement that the matrix elements are given by the fusion kernel. So this is an exact statement because it's a mathematical statement. I mean, there's no physics there, but here you need to say like when is this valid. So in general, this is valid when the energies are large. Okay, so this is the derivation of the Cardi formula. I mean, is there any questions related? Okay, so then we can go roughly to the 3D gravity calculations. I think one of you already know that like how I am reducing 3D gravity to Liouville CFT, but let me just write it anyway. So let's say I want to compute the black hole that solves the boundary conditions for the 2-point function of the CFT line defect. So there's a line defect here and then its conjugate here, and I told you that the way to do it is to fill in this boundary conditions with the suitable bulk geometry, and the line defect sources a shell, and this resulting geometry is obtained by gluing a portion of BTC to a portion of empty ADS. So that's the 2-point, that computes the 2-point function in vacuum. So now to explicitly evaluate this 2-point function, I can do this slicing, this hyperbolic slicing, where these are the slices. So now each slice is like a semi-infinite cylinder with a line defect inserted. So that is each slice in that hyperbolic slicing, and I know that each slice is described by this Liouville solution.
What is happening at the starting point of the slice?
So that's ZZ. Yeah, that's the key point. That's why the ZZ is related to the black hole. Okay, so let me sketch the proof, like how to show that the 3D gravity calculation actually reduces to Liouville.
And is that because you're going to the boundary?
Yeah.
Which one of these or doesn't matter? They're all complicated.
Yeah.
So it doesn't matter.
Yeah, I mean, it doesn't matter where the Liouville is living, but it matters where the CFT is living. CFTs live on the boundaries, but Liouville lives anywhere.
So what did you say about this being on the boundary and that's what it's
That edge I thought was on the boundary of ADS.
Yeah, here.
And so the field going, boundary conditions in ADS are this.
Yeah. Okay, there's a very simple form of the metric in the slicing. So this is the metric on the black hole, in this slicing. As you can see, it's quite general. It doesn't even matter what the Liouville field I'm using. It's like I could have shells or particles or topology or whatever. So what this is saying is that so each of this rho equal to constant slice is described by uniformization, and then what this coordinate, this cos squared rho is like a warp factor that only changes the size of these slices. Yeah, but that doesn't change the intrinsic geometry of the slices. So now all you have to do is you have to plug this into the Einstein-Hilbert action. Oh, sorry. Okay. So you still have to check that this satisfies the Einstein equation. So if you solve the Einstein's equation, yeah.
Will live in the boundary?
Yeah, for these kind of examples, yes, correct. Yeah.
Because in that one, you explain why the identity always runs, right? It's like
Yeah.
you're just picking some fake
Correct.
locus on the boundary to help your quantize.
I see.
To help you quantize, right?
Yeah.
But actually there is nothing there. Yeah.
I mean that's like a bulk intuition for the fact that there's only the identity, right? It's not. I don't know if it's. Yeah.
This metric is a solution of Einstein equation and phi satisfies the.
Yeah, exactly. I was about to write that. So if you plug this metric into Einstein's equation, it shows that Liouville equation. So Einstein's equation implies the Liouville equation. So yeah. I mean, even otherwise, you know that this has to be hyperbolic for this to be a solution to Einstein's equations, and the condition of hyperbolicity is the Liouville equation. So yeah, it's not surprising.
This is a very clear connection.
Yeah, very
gravity
and Liouville CFT. Yeah, and in fact, you can actually compute the action. Sorry, actually, another check you can do is you can compute the Brown-York stress tensor of 3D gravity on the the Brown-York stress tensor, which is like defined in terms of the extrinsic curvatures, Kij minus Khij plus Hij, I think. Yeah, so I mean roughly there are some factors here. So you can compute the Brown-York stress tensor for any of the solutions described by this metric, and it turns out to be given by the Liouville stress tensor. So stress tensor associated with the Liouville field. So that's another check that the Liouville solution is actually like governing the dynamics of these geometries. Okay.
Here the stress tensor is being, the Brown-York stress tensor is being computed in the rho direction.
In which yeah, on the boundary, it's like the CFT stress tensor, but yeah, it's the CFT stress tensor. Yeah, this is the statement. The CFT stress tensor matches with the Liouville stress tensor. Okay, and you can actually plug this into the gravitational action. So the gravitational action is well, I've set the ADS scale to 1 and chosen the cosmological constant to be like -1 or something. So then so this is the bulk term and this is the GHY term at the boundary, and this last piece is a ADS3 counter term. So you just have to plug this solution into and evaluate the action, and it turns out to give just the Liouville action. It's a quite general result. I mean, now it's not surprising, right? Because it solves the Liouville equation and also the stress tensor is the same. So it's not at all surprising that this gives the Liouville action. So one thing I should mention is that whenever people are doing calculations in 3D gravity, they say that the GHY term can be ignored and like can be removed by counter terms, etc. But to arrive at this result, it's very important that both of these bulk term and the GHY terms combine together to give the Liouville action. Yeah. So this is not just true for black holes, it's also true for wormholes, for two boundary wormholes. So as I said, like if you make the slice compact without a boundary, then it's a genuine two boundary wormhole. So you don't have to worry about introducing ZZ brains or anything. So it's like literally the topology would be something like this: a sphere times an interval, and with some matter running. Let's say there's like a point part, the world lengths of 2 point particles, and like there's a shell. Now again, if you use this form of the metric, then all I need to care is about the Liouville solution on the sphere, which is punctured twice by these local operators and once by the line defect. So, and this is the reason why this was giving rise to this C0 formula. Why the Liouville structure constants are equal to the gravity partition functions. I mean, does this require more explanation, or do you agree? I mean, the fact that this is equal to this. So there's like, so this is gravity, and this is Liouville structure constants, or Cardy formula, whatever you want to call, and then this is equal to the statistics, the variance of the matrix elements of the line defect d sigma.
And this averaging is over the HIH.
Yeah, okay. So I guess that will come back to the discussion. So I'll go to the discussion of averaging. Yeah. Okay, so this is a formal average, as I told in the first lecture. So whenever I write this in, whenever I describe the CFT ensemble, I am describing it very formally, where I am not really giving you like what I am averaging over to get these results. And the reason why I have to do it formally is because the space of CFTs is not known. And I don't even know what measure to put on the space of CFT so that I can explicitly realize this average.
Sorry, but just like Cardy formula, why can't we say it as a coarse-grained?
But coarse-grained for individual boundaries, but here like you have two different boundaries, right? I guess yeah, as we discussed, like.
But the statement is true also for single statistics of.
Statistics,
right?
yeah.
Cardy formula is okay. Now you are.
Exactly. I'm explaining something else. Okay, so I want to point out the distinction between two different things. One is coarse graining, which is microcanonical average. So that is something that is always present, whether you consider single boundary or multiple boundaries or so on. Because if you want to make sense of expressions like this, where on the left hand side you have quantities which have discrete labels, whereas on the right hand side you have quantities which are continuous functions of weights. So you need some amount of averaging over some energy window surrounding these operators. So this is always present. So that's why I won't even write the bar for this. I think that was confusing when I described it in the first lecture. So this is always there. So even when I describe multiple boundaries, observables, like when I consider products of partition functions and so on, so this kind of averaging is always there. But there's something else on top of that, which is this formal average. That is what is called the ensemble average. So the question is, how do we specify the ensemble? The general answer is we don't, because we don't know what the space of CFTs is.
This is averaging over different CFTs.
Yeah.
Different CFTs which have the same
corresponding spectrum. Yeah. So if I can formally specify the ensemble like this, like by specifying the spectrum and specifying the OP coefficients, and I say that all of them have the same spectrum, and all of them have like the corresponding OP coefficients, and I'm computing the statistics. So that's I am computing these formal averages involving the OP coefficients or matrix elements of the line defects. Okay, so one way to one way you can try to make this more explicit is when your CFT admits marginal directions.
Why is it clear that if you have the same spectrum and the same set of OP coefficients, that there is a degeneracy between the theories?
I'm not saying there are same set of OP coefficients because what I'm computing is the variance, right? It's like I'm computing like the correlation between the OP data of like different members of the ensemble, and I'm averaging over that.
So the ensemble is specified, right?
The OP data. Yeah. Okay. Okay. So one way to make it explicit, as I was saying, is if your CFT admits marginal directions. So let's say there's a marginal scalar in the spectrum of your CFTs. In that case, there's a moduli space of marginal deformations, and there's a natural metric on that moduli space, which is given by the Zamolodchikov measure, which is nothing but the 2-point functions of the marginal operators. So that is a very concrete example to average over. So in that case, even the ensemble is like neatly specified. It's like the ensemble is a space of CFTs on the moduli space of marginal deformations.
But you require the ensemble to have the same spectrum.
Yeah, that is an assumption I'm making.
But in general, that won't be true in this case.
Yeah, in general it will not be true. But
This
exactly. If you as you move around sufficiently far away, then you have anomalous dimensions and so on. So you cannot expect the same spectrum. But if all I'm assuming is you are when you're doing the average, you are doing the average over a small enough window around a point in the modular space, so that you don't have to worry about these effects when you go to different points in the modular space. Okay.
I mean, if the region is small enough that the deltas don't change the CFT, so it will also.
That may be true. Sir, you might as well not average, you're saying.
Because it's not like if you're sampling things very close, so that the deltas don't change. I mean, I don't know what happens at time.
Yeah. Maybe the pickup phases which are dependent on the location. Yeah.
But why do you insist on deltas being the same? I mean, if you are, as you said, that average always present.
Yeah. Correct.
So why do you insist that the deltas are same on some?
Well then, I see. Yeah. Correct. Yeah, that's right. Yeah.
No, what was that? As long as you can make a one-to-one map between states in one and the states in the other, I think that's it.
Yeah, that's a sufficient assumption. Yeah, I think what I said was maybe stronger. Okay, so if you have a marginal direction, then let's say in the bulk, what you the theory that you are working with is like Einstein gravity minimally coupled to a massless scalar field. This is like the simplest way to introduce a marginal direction. Introduce a massless scalar field in the bulk. So if this is the bulk theory, and all these wormholes that I constructed will be solutions to this theory as well. So there were solutions to this theory where there was no scalar field, but there are also trivially solutions to this theory.
Because phi is 0.
Because you can set phi to be uniform. Like it doesn't even have to be 0. You can set it to be uniform, and they're always solutions. Okay. So then what I can do is, let's say I take this wormhole, and now I introduce this dilaton value. Let's say it's uniform, and this wormhole is a solution for any value of phi, this uniform, any value of the dilaton. So this phi 0 could be anything. Okay. So then I can formally define this average as an average over a small window around phi naught. So I can define this average by integrating over a small window around the values of the dilaton, or the values of the dilaton correspond to marginal couplings on the two boundaries. So I can average over left and right, and then there's a canonical averaging measure. It's because the wormhole solutions exist only when the values of the dilaton are the same on the two boundaries. So what I can do is I can just set the fluctuations on the two boundaries to be the same. I think this, you were also discussing something like this, right? Where if there's a canonical measure to average over, I think there's a canonical measure here. And even for multiple boundaries, I just have to set the fluctuations. So what I'm doing is I'm actually binning, right? So I'm averaging over a small window around phi naught. So let's say I'm averaging phi naught minus delta phi over 2 plus phi naught plus delta phi over 2. So even if you have multiple boundaries, all I have to do is I have to set the fluctuations on each of the boundaries to be the same by these delta functions, and then this is like a explicit way to realize this average.
And if delta phi went to 0, you would get no correlation.
Yeah, delta phi goes to 0.
If you had no binning, if it was just one theory, you would get no correlation.
Because you can independently do the two integrals?
Because then it's gone back to the case of one theory. Again.
Yeah.
Okay, so now the answer has to sensitively depend then on delta phi.
Correct, yeah.
So how do we choose delta phi?
I mean, you were asking how small should it be?
Yes.
Yeah.
Compared to the kind of averaging we get automatically from Cardi. You know.
Yeah.
It
Well.
has to be more or less the same, right?
Yeah. It should not be very sensitive to the size of the window. Yeah.
But what confuses me is that if you set delta phi to 0, it looks to me like you're getting just no correlation.
Well, if you're setting it to 0, then what am I actually averaging over? There's nothing, right? Yeah.
So that's what I mean.
Yeah.
So since 0 tells you there's nothing, 0 would be like some infinite action for the wormhole or something like that, right? So then it seems to depend sensitively on delta phi.
That part I don't understand, because there's a wormhole where you just set the value of phi to be, say, left phi naught. There's no delta phi here. So phi naught on both boundaries. There's no fluctuation, but all these are solutions.
That's from gravity.
From gravity, yeah.
So let's go to the field theory.
Okay, let's go to the field.
Suppose delta, so then delta phi is 0, so that's just one value of phi naught.
Okay, yeah.
Then if it was just one theory, aren't we back to the same puzzle?
That's right. Yeah, I guess you need to introduce some non-zero value of delta phi to make sure.
If 0 is special, if 0 doesn't work, then that tells you it sensitively depends on delta phi.
Maybe this is a stupid question, but I was just thinking that in a single boundary case, you said there's this kind of averaging always present. Right?
Yeah.
So why can't
It be in the two boundary cases.
why can't that?
It just seems like what you're doing here has nothing to do with what you're
Yeah, so
Yeah.
see that averaging is always there, so I think it's in Z of beta. I mean, whatever the way you have defined Z of beta, that's what it is.
Correct, yeah.
It's different if you introduce a time, beta plus IT and beta minus IT.
And do the average over time. Yeah.
That's a slightly different issue, right?
Yeah.
And in this two boundary case, it would be a separate, coarse graining of C and a coarse graining of C.
Correct.
That is different from that.
Yeah, that's right. If you independently coarse grain, then you get 0 or something. Yeah. So you have to coarse grain in a correlated way to get the answer.
Okay, but it's nice this.
Yeah.
But okay, so this is a model, right? A particular
Model.
proposal.
Yeah, particular proposal. Yeah. It's not like the most general. This is, in fact, I would think that this is the only way we can make sense of averaging in higher dimensions, because you need some space to average over, moduli space, and marginal deformations are the only thing that I can think of.
Infinite grain theory has no marginal deformation.
Okay, I don't know.
N, there's always N.
Averaging over n. Okay, yeah, that may.
Yeah,
I see.
somehow
Yeah.
that's intrinsic to the fact that we're getting gravity.
I see.
We only get gravity at large, therefore we should use N.
To average
Averaging
over.
over N is really like averaging of the coupling of the bulk theory.
Not this coupling though, because this
Not
coupling, this coupling actually determines the G Yang-Mills, for instance. So what you're doing is averaging over Yang-Mills couplings.
In the infinite grain theory, there's no bulk coupling.
Right.
Right? It's just averaging over number of fluxes.
No, but like if you introduce brains and stuff, then there's no factorization possible, because that's like a dual to an individual theory. So I don't really see like all this discussion. If there are wormholes, but then there will be other contributions, because see, this is a theory with no brains, so that's why like I didn't consider many exotic contributions where I introduced brains in the bulk and so on. So
this is about brains in the bulk. I was talking just about M5 brain theory,
Yeah.
6-dimensional 2,0 theory.
Oh, I see. Okay.
Super conformity.
Oh, sorry. Okay. So okay. Yeah. I see.
The property of that is that it doesn't have any deformations.
I see.
Maybe that
Well, it
doesn't
doesn't have
admit
deformations
wormholes.
preserving supersymmetry.
How do we know if there are?
But there is representation theory study of such things. I don't know what is the answer. But at least with preserving supersymmetry there are none. But maybe breaking supersymmetry can allow.
Preserving supersymmetry, there are no wormholes.
No, there are no deformations.
There are no deformations. Yeah, of course.
Yeah.
There's no one.
But I mean, it's not like we have to average over
But
supersymmetric.
At large n,
Just one hole probably just throw the supersymmetry out of the window anyway.
yeah. But okay, we could study that, but I don't think. I mean, at large n, it would have to be a marginal scalar at the bulk. So just the question is, are there bustless scalars in the bulk? There's no dilaton.
Yeah. I think that Clay and Integrator and all, Thomas, they looked at this.
They looked at this, yes.
I don't. Okay, so from the bulk point of view, I don't know, but at least this
Just from supersymmetry, yeah. But we could easily, it's a Kaluza-Klein spectrum.
Yeah.
Could easily figure out.
Yeah.
Okay, I think there is no. I'm pretty sure that there is no massless scalar that preserves SO whatever. Right, SO5. The asymmetric group. Because all the other scalars will come from Kaluza-Klein. They will all transform under the SO. Right. So,
Yeah. So, I mean, that is like making supersymmetry roughly, right?
okay, but you would say let it be.
Yeah. In non-linear.
Okay, maybe the analog of the 20. No, but that is. Okay, you know. But it's unlikely it's exactly marginal. Do you want exactly marginal for this?
Yeah. I see. Okay.
Although n equals 4 has exactly margin, n equals 1 preserving some deformation.
Correct.
So it's not so unlikely. I don't know. I mean, one has to see.
Okay,
There are representation theory reasons why not totally non-supersymmetric, but some supersymmetric preserving deformations can be.
I see. Maybe.
In the recombination rules.
Okay, so that's basically what I wanted to discuss, but since I've introduced this model and I have like a few minutes of time, I'll just describe some nice solutions that this model exhibits. Okay, so these okay, so some of this result just appeared in the paper that I wrote today, which came out today. So
You wrote a paper?
yeah. So in that paper I just considered solutions to this theory where there are different values of dilaton on the two boundaries. So let's say phi 1 and phi 2. So this theory also admits such solutions, and these solutions are locally described by the Janus domain wall solutions.
So you have this theory in the boundary and you're considering those geometries where sphere.
You can consider any geometries, any two boundary wormhole.
You don't want hyperbolic.
I want hyperbolic.
That's hyperbolic.
That's hyperbolic. Yeah.
With the punctures.
With punctures, yeah. Or I could just consider like for any two boundary wormholes.
Yeah.
Okay. Let's say phi 1 and phi 2. So on the CFT side, what I want to, the question that I want to ask is, so this is computing the partition functions, the CFT partition functions of two marginally deformed CFTs. So this wormhole is a contribution to the product of partition functions in marginally deformed CFTs. And yeah, there's some amount of averaging, like as I told, like a small window around phi 1 and small window around phi 2. Okay. So now I can ask like how correlated are these two CFT observables in these two CFTs. So naively what you would expect
So
is
small window on phi 1 and phi 2, they are equal. Right?
yeah, the canonical measure, yeah, okay. So I can ask like how correlated are these two CFTs. So naively you would expect that if the difference in these couplings is large, then they are less correlated. So let's say phi 1 and phi 2 are marginal couplings on the two boundaries. So let's say they are like infinitely far apart, like phi 1 is very different from phi 2. Then I would say this correlation should be very small. So that I can prove it using using the wormhole. Let me just write down the result for you. So the result is the following. So let's say I'm computing the correlation between CFTs of phi 1 and phi 2 average, and that is equal to cosh of the difference delta phi times the Euler characteristic of the Riemann surface. So I'm computing the partition function on a Riemann surface, right? So the Euler characteristic of that Riemann surface times the product of partition functions when there is no difference in marginal couplings, when delta phi is 0. So this is the result. So clearly if you observe this result, you know that hyperbolic surfaces have negative Euler characteristic. So that means you see as delta phi increases, the correlation decreases and goes to 0 when the difference in phi's is like very large. So that's so the way I prove this result is by doing a gravity computation that corresponds to this wormhole geometry. Okay, so
Sorry, just before that, just a stupid question.
Yeah.
So if you just have that kind of a theory, simple theory in the bulk,
Mhm.
right?
Yeah,
And then you're saying thinking of this boundary value as a parameter, right?
yeah, correct.
So from the CFT, what is this? I mean, what is this simple CFT with some more exactly marginal parameter? I mean, is there some? Is it just like a free field? But free field, what kind of parameter?
N equals 4 n.
N equal to 4 yeah, with two different coupling constants. Like you, okay, so these are
So not just this theory, right? Not just this theory. This is like a free theory.
no, this is not a free theory because there are all these stuff and it has this topologies, right? So there are like heavy operators running. Yeah, I don't know if you can call it free theory. Yeah,
Some holographic CFT.
some holographic safety. Yes.
No, I mean, I was thinking that the boundary Lagrangian is just this. A bulk Lagrangian.
Now, I think this is the path that will appear in his gravity solution.
Yeah, exactly. That's yeah,
There's a consistent truncation.
yeah,
In N equals 4 it would be like.
exactly. Yeah. I'm turning off the sources for the other fields, so I'm only turning on the sources for the dilaton. So I mean I'm doing this progressively. So you see, like I started with this Lagrangian and then derived all those gravity solutions, and now I'm turning on the source for the dilaton only, and then I'm looking at those solutions, and those solutions are giving me this nice physical property that they can understand how correlated CFTs are, different CFTs are. Okay, so the way I do this computation, I'll just sketch this. I have to write down a metric on this geometry. So I write down the metric in the following way. So it's of the same form, d rho squared plus some warp factor times Liouville field. But just that this warp factor is different from cos squared rho, because now there's a deformation. Like each of these slices is labeled by a different value of the scalar field. So this is something. In fact, in this case, it takes a very simple form: 1 plus cos 2 rho divided by cos delta phi. It's as simple as this. Because you see, if you set delta phi to 0, you get back cos squared rho. So in that sense, this kind of solutions describe an RG flow, because the local curvature radius is changing as you move from one slice to another. So like you could say the central charges are changing when you move from one slice to the other. But when you come back to the same boundary, because of the symmetry, rho going to minus rho symmetry, the central charges of the two CFTs on the boundaries are still the same. Okay.
But there's no sense in which when delta phi goes to infinity, this thing disconnects.
This morally that's what this is saying, right? Because the correlation is 0, so it's like it's totally disconnected. And the reason why it disconnects because the volume of the wormhole becomes infinite.
Oh, okay.
Yeah. Okay. So I can compute the action for just like how I computed the action for these kind of wormholes, and it very nicely turns out that this deformation only couples to the topology of the Riemann surface. It doesn't couple to the moduli.
Sorry, the rho at the two boundaries is what?
Minus infinity and plus infinity.
Minus infinity.
Yeah.
So I think the geodesic distance between them is probably going to infinity.
Yeah. That's right. Okay. Well, I mean, these are already at infinity for each value of deformation. So it's like the renormalized geodesic length itself is going to infinity. Yeah.
When delta phi goes.
Yeah, when delta phi goes. Yeah. So because the volume of the wormhole is always infinity. But you can extract a renormalized volume of the wormhole, which is finite. But now, if you take delta phi to infinity, the renormalized volume itself becomes infinity. So that's the point. Okay, so this deformation is special because it's sort of uniform over the Riemann surface. It doesn't see the moduli of the Riemann surface. It only sees it only sees the topology. In other words, it only couples to the area of the Riemann surface.
Does this in the middle? Does this Riemann surface become very small?
Yeah, because of the warp factor. So the Riemann surface is big at the boundary, becomes small in the throat, and then again becomes big at the other boundary.
But when your delta phi goes to
when delta phi goes to infinity, it's uniform, you see, because if delta phi goes to infinity, this term just vanishes. So it's like d rho squared plus half times e to the phi times d sigma squared. So the Riemann surface never shrinks, it's like uniform everywhere.
So you renormalize the volume by subtracting something? Or what?
Yeah, you renormalize the volume. So way you compute the volumes is by regulating it. You introduce a cutoff here. And then you renormalize by removing the terms which are divergent in that cutoff in an appropriate way. Holographic renormalization. Yeah. Okay, so if you compute the action for this wormhole and then subtract the action of the undeformed wormhole, it's very nicely, it's just proportional to the Euler characteristic of the Riemann surface times whatever the cos delta phi. So this is the result. So in other words, all this Liouville part just drops out because since this deformation is not sensitive to the moduli, the Liouville part drops out, and you only get the Euler. You get the area of the Riemann surface, and you know that the area is determined in terms of the Euler characteristic. So this is the result, so this is the gravity result, and then you interpret it in terms of the CFT, and it says that the CFT correlations are dying as the difference in marginal couplings increases. In fact, in this case, you can even average over the entire modular space. So the way to do that is you can compute the analog of the Zamolodchikov metric. So the Zamolodchikov metric is nothing but the 2-point function of the dilaton. But now you can compute the 2-point function by inserting a dilaton here and here. One dilaton insertion here and the other insertion here. And actually what you are actually computing are integrated dilaton correlators. So what I am computing is the integrated dilaton 2-point function. So this is the 2-point function where one insertion is on one boundary and the other is on the other boundary. So and I am integrating this over the Riemann surface. And this actually turns out to be secant hyperbolic squared times delta phi. I mean, you can understand why this is the case, right? Because the partition function of the wormhole is of that form, and you can just differentiate the partition function, the log of the partition function twice with respect to the marginal coupling, and that will bring down two dilaton insertions, and that will give you that result. I mean, if it is confusing, I can explain some more steps because what this is just the GKPW dictionary. So I'm just differentiating the wormhole partition function with respect to this dilaton sources on the two boundaries, and since the sources are uniform, it is going to bring down an integrated correlator, the value of the dilaton integrated over the Riemann surface, and that is equal to this simple form secant hyperbolic squared times the difference in marginal couplings. So this is like a natural metric to average over the moduli space. So I can actually take this wormhole amplitude now, which is expressed in terms of cos delta phi, and then I can average over the moduli space with this being the measure. So I can compute like average quantities in this way. Yeah. So. And actually this storage generalizes to higher dimensions. You can take let's say you take 2 copies of n equal to 4 and with different marginal couplings, and you can actually compute the volume of the wormhole that joins the two, and you can show that the volume of the wormhole again increases in the same. I mean this function will be more complicated, but again it's a monotonic function. It monotonically decreases with the difference in marginal couplings, and so even in higher dimensions it's the CFTs are getting increasingly decorrelated as the difference in marginal couplings increases.
Is this the first example of an n equals 4 wormhole that has been reliably computed? It sounds really interesting. You were telling me it's the Janus solution.
It's the Janus solution. Yeah, it's an orbifold of Janus solution. I mean, people have tried computed with different boundaries, like S1 times SD minus 1, for instance. But I don't really understand like what it is computing exactly. Maybe it's computing correlation between partition functions instead of like a correlation between correlation functions. Maybe it's computing like the correlation between thermal partition functions. But
so this wormhole is hyperbolic?
This is hyperbolic. So with those topologies, it's generically not hyperbolic. So they play some games which I don't completely understand. They call it constrained instantons or something. They fix the energies and so on.
This is much cleaner. Right?
Yeah, this is very clean. Yeah.
Sorry, but in n equals 4, what is the solution that you are computing? With what boundary going to what boundary?
So n equal to 4 placed on a compact 4-dimensional hyperbolic surface.
Any hyperbolic?
Any 4-dimensional hyperbolic surface. Let's say simplest class of examples is take H4 and you construct a quotient of H4 with a discrete subgroup of its isometric group. Any it works.
Then you can this wormhole exists like that.
Yeah. I mean you construct it in a very similar way.
I see. So maybe you look at I see. So you basically think of the whole thing as the quotient of ADS5 probably, right?
Exactly. It's a quotient of ADS5.
Boundaries are also foliated in a way that they are 4-dimensional hyperbolic
Correct.
spaces. And this quotient then acts on both the bulk and the boundary together, giving you the compact and the.
Correct.
And you start with the Janus solution.
Yeah.
Which has coupling one here, so one coupling here, the other coupling there, and now the boundary only misses the singular part.
Yeah.
Because of the quotient.
Sorry, but then this Janus solution, these are like field theory things, right? Or what is it?
No, they're a gravity dual.
The gravity duals of interface CFTs.
So
It's a solution for coupling constant changing abruptly.
Abruptly across an interface.
There's a singularity and you're saying about the singularity?
By quotienting, yeah.
Then you have to take that and further quotient it to get like compact hyperbolic.
No, so let's say the boundary is like this.
Because you want two different coupling constants.
yes.
Okay, so let's discuss the Janus solution. So that's a bulk solution with a single boundary, and the boundary is like say RD. Then these two half planes are like, I can call it as the HD and HD bar, like upper and lower half spaces, and there's an interface that separates between them, codimension 1 interface. Now the Janus solutions solves these boundary conditions with different values of the Yang-Mills coupling. So you fill this with the bulk solution with different couplings, and the transition is abrupt in the CFT because there's a jump across this interface, whereas it's smooth in the bulk because the dilaton changes smoothly. So it's like a continuous domain wall solution. So that's the Janus solution. So what I'm doing is very simple. I want to convert this into a 2-boundary wormhole. This is a single boundary solution, but I want to convert it into 2-boundary wormhole. So for that, I need to prevent these two half planes from meeting. So the way I can do that is to take quotients. So I can take a quotient of HD by some subgroup of its isometric group to get some compact space, and I can do the same quotient here to get another compact space.
Oh, I see.
Yeah. And now the resulting geometry is a 2-boundary wormhole.
these are two separate quotients or what?
Yeah, two separate quotients you could say. I mean, or you could say like I'm taking the entire solution, the bulk solution, and then I'm quotienting it by the same subgroup.
No, but usually when you quotient the fundamental domain,
Yeah.
is connected one, right? Or not?
No, it's kind of, yeah, it's I mean, I don't know, if you think of this as H2s, then let's say I'm taking a quotient of H2, this gives me the genus 2 fundamental domain. So this, let's say this is a genus 2 fundamental
No, I
domain.
mean saying, so you have two domains, right, on the boundary, that one and that one there.
Yeah, but the bulk is connected.
No, I mean just look at the boundary.
Yeah, the boundary has two. The boundary, it's like separate quotients, yeah.
Separate, well, it's the same, is the quotient by the same.
It's the same group, but I'm quotienting the two half planes separately. Okay, let me just say,
It's a subgroup that preserves
exactly, it preserves the radial direction. Yeah.
And then
Yeah.
you have two of them.
Correct.
Yeah, okay.
So let me just write it very schematically. So let's say I have HD plus 1 and I'm quotienting it by a subgroup gamma, where the subgroup is a subgroup of the isometric group of HD. Okay, and then that is sort of equivalent to quotienting HD by the subgroup, then times an interval. So
And that interval is in the bulk.
that interval is in the bulk.
That's very clever.
Yeah.
It's so simple.
Yeah, very simple. Yeah. But this Janus solution, is it it's non-trivial, metric, etc.
Completely.
changes? Yeah. So not hyperbolic in particular, right?
It is hyperbolic. It's a solution to Einstein's equations. Yeah.
No, but constant curvature.
I mean, it's a sort of it has a similar form like this. I mean, it's slightly more complicated. I mean, I can write it down for you if you want. It's like there's a similar radial coordinate. Times something like this. So U plays the role of rho.
The Riemann tensor would be different, right?
Yeah, of course, yeah. I mean, I don't know if you can use the same ideas like uniformization and so on, because this is higher dimensions. Maybe these are not conformally flat. There it was like all two-dimensional metrics are conformally flat. So I can write it as lu e to the 5 times dc squared. But here I cannot do that. But it has the same form as this, because the role of the radial coordinate rho is being played by U, and then this is the metric on the compact on this hyperbolic space. Yeah, it's the same as the upper half space metric. Yeah.
And notice that if you want phi1 equals phi2, you don't even need Janus. There you just need ADS5.
It's a ADS5. Yeah. So the thing is, the reason why this quotient, like when you're doing this quotient, you should be careful that the dilaton profile may not be smooth under this quotient. But in this case, since the dilaton was uniform over HD, the quotient does not affect the dilaton profile.
No, but sir, in general, why is it that the bulk preserves the subgroup with which you're quotienting?
In general, it's not true, but in this case, where the dilaton profile only depends on the rho coordinate instead of the transverse coordinate. Yeah.
Like those planes and
Exactly.
changes that.
Yeah, I do this foliation again, like this hyperbolic slicing. Yeah.
And then everything is same on that.
Yeah.
Those slices.
Yeah.
And then that's how the
Correct.
symmetry acts on the
Correct.
slice, yeah.
Correct. Yeah, so in the paper I've explicitly computed the volumes of these wormholes in terms of hypergeometric functions, and I showed that those volumes are monotonic. So that proves, so volumes being monotonic proves that correlations decrease monotonically.
This discrete subgroup is a discrete subgroup of the whole bulk.
It's a, yeah, so it's a subgroup of HD, but I am like embedding that into the subgroup of the full bulk isometric.
It's like a discrete isometry of the whole bulk.
Yeah, correct.
You just want to.
Yeah. Yeah. I guess that's all I wanted to say. Thanks.
Any more questions? If not, let's thank Jivan again for the wonderful.